Good afternoon, Organizing Committee. I'm honored to present our research paper titled Revolutionizing Fast Food Classification, a convolutional neural network approach for enhanced nutritional awareness. The authors of this research paper are Dr. Mrugendra Revar, Dr. Atul Patel, Mr. Dev Gundalia, Ms. Keya Patel, Mr. Vatsal Doshi, and myself, Nirava Parikh. And together, we are representing Charotar University of Science and Technology, Anand. I would like to thank Reva University for organizing this seminar and ICICDS for accepting our research paper. In this paper, we delve into the intersection of technology and nutrition, aiming to address the pressing need for improved awareness and understanding of the nutritional content of fast food options. Next slide, please. In this presentation, we would be talking about the important topics in the following chronology. Starting with introduction and related work, we would be moving on to an overview of the dataset selected and the model chosen. Finally, a brief about applications and before concluding the presentation. Next slide, please. Food is essential for human survival, providing vital nutrients like protein, carbohydrates, vitamins, and minerals. Global food consumption in 2022 was 2,571 billion metric tons with a rising trend. There is a growing demand for food recognition systems to evaluate nutritional components and plan dietary meals. The FMCG sector plays a significant role in the global food industry. Food classification is crucial, driven by increased health awareness and the need to monitor dietary intake. Modern day issues like declining produce quality and child malnutrition highlight the importance of food classification systems. CNNs are effective for image identification and classification tasks. Next slide, please. Some work has already been carried out in this sector. Researchers working on it implemented SVM algorithm using the SIFT method and the color histogram method. Many Indian researchers like Dr. Vishwanath C. Burkapalli also worked on the recognition and classification of images of Indian food. He used histogram-based color and texture feature sets for food descriptions. The local binary pattern LBP operator was used for texture features. We have taken inspiration from all this research carried out earlier and taken it further in our research paper. Now, my co-author, Ms. Keya Patel, will carry on with the presentation further.
Okay, thank you, Nirva. So now we will be discussing about the data set which we have used in our model. So in fast food classification, we have used 10 distinct classes representing different fast foods in it, like burger, crispy chicken, fries, taco, donut, hot dog, pizza, sandwich, taquito, and baked potato. Right hand side is the uh, pie chart which represents all those fast food classes that we have used along with the proportion in percentage. We have also mentioned the link from where we have taken the data set, that is from Kaggle website. Um, so the TensorFlow record contains training and validation images. The image here are resized to 256 by 256 pixels. The data set is majorly divided into training, testing, and validation set, wherein the training set consists of 15,000 training images with 1,500 images per class, each class represented by a separate subdirectory. In testing set, it consists of about 1,500 testing images, ranking from 100 to 200 images per class, whereas in validation set, it consists images for model validation and 3,500 validation images, 400 image per class. Right hand side are some of the few images which we have used in our model. So in version 2, we have extended the number of classes by adding 5 other classes in it, which are of baked potato, crispy chicken, fries, taco, and taquito. So in our fast food classification of version 2, in total, it consists of 10 categories of fast food classes. The total number of images are 20K. The training image count is 15K, and validation image count is 3,500. Testing image count is 1,500. So the major difference between version 1 and version 2 is that version 2 is more comprehensive and diverse compared to version 1. Version 2 also includes more classes, images, validation, or testing images than version 1, enhancing the dataset comprehensiveness and diversity. Now, I would like to pass it over to our co-author, Mr. Dev Gundalia.
Thank you, Keya, for overviewing the dataset description. Now let's move to the proposed architecture of the following research paper. So proposed architecture for the following research paper is convolutional neural network mobile net. So let's talk about mobile net. What is mobile net? Mobile net is open source model made by Google. MobileNet is uses a CNN architecture model to classify images. It has been pre-trained model over the 1.2 million images for the classification task, utilizing the pre-trained MobileNet V2 architecture from the ImageNet dataset. Now MobileNet V2 is refined version of MobileNet V1. This makes it even more efficient and powerful than the previous one. It uses less computation power to run, and also is trained using a large image dataset, that is 1 million, more than 1 million images. This architecture that we have used comprises a series of depth separable convolution layers, a kind of convolutional neural network layer known for its ability to achieve notable accuracy while using fewer parameters and computational cost. The model further incorporates a global average pooling layer, which works to decrease the dimensionality of the output originating from the convolution layers. Now let's talk about the results section of this model, proposed architecture and the model. So results about training and validation accuracy. Let's talk about the accuracy first. So training and validation accuracy for 30 epochs. After running the 30 epochs, we got 87.6 percentage and 83.31 percentage respectively for training and validation. Talking about the loss, we our training loss was around 0.3995 and validation loss was around 5642, indicating a good generalization over the model. And our matrix is confusion matrix. Confusion matrix, our diagonal components show how accurate predictions are, and non-diagonal elements reveal misclassification that basically shows errors in fast food classification during the training. And talking about the specific performance, competitors observed in specific classes, that is class 1 and class 6, challenges encountered, particularly with class 9. It suggested us that we should fine tune our hyperparameters and provide more training data for class 9. Utility of confusion matrix, evolution tool for classification model efficacy, helps identify areas of proficiency and improvement, facilitates informed strategies for accuracy enhancement for our model. So now let me hand over to our next co-author Vatsal Doshi for following outline.
Thanks, Dave. I'll be explaining the application. A model that accurately classifies fast food items from images can have various current and future applications, particularly in the domain of health, food, and technology. It's some of the possible implications in industry are health and nutrition, dietary monitoring. Individuals can make the model to make their food intake and more information about their dietary choices by monitoring their consumption of fast food items. Nutrition analysis, the model can provide insights into the nutritional content of different fast food items, helping individuals make healthier choices based on factors such as calorie count, fat content, and sodium levels. Can you move to the next slide, please? Fast food industry quality control. Restaurants and fast food chains can use the model for quality control purposes, ensuring consistency in the appearance and presentation of their menu items. Menu recommendation system. Food delivery platforms and restaurants can leverage the model to recommend menu items to customers based on their preference and previous order. Retail and marketing. Personalized advertising. The retailer and investor can use the model to deliver personalized advertisements and promotion for fast food items to consumer based on their preferences and purchasing behavior. Can you move to the next slide? Yeah, product development. Food companies can utilize insights gained from the model to develop new fast food products that cater to consumer preferences and dietary trends. Healthcare. Dietary counseling. Healthcare professional can use the model to assess patients' dietary habits and provide personalized dietary counseling and recommendation for managing health conditions such as obesity, diabetes, and cardiovascular disease. Public health initiatives, government and public health organizations can leverage the model to monitor trends in fast food consumption and develop targeted interventions and policies aimed at promoting healthier eating habits. So now we'll be talking about the conclusion. Model performance. CNN model achieves 87.06 training accuracy and 83.31 percentage of validation accuracy. Applicability and impact. Model shows potential in food industry for crafting healthier options. Consumer can make informed dietary decisions using the model. Researchers can analyze fast food nutrition composition, future directions, expanded dataset, and integrate real-time detection. Design user interface for enhanced interaction. Potential application, healthier food choices, calorie monitoring, allergen identification. Overall significance, promising approach to fast food categorization with notable precision, holds potential for substantial impact across various fields. Thank you for listening to us, and that's all from our side. If you have any questions, then you can ask to us. Thank you.